Hi everyone, I'm Liew Wen Yen and my partner Chung. We are excited to present our project on loan default prediction using machine learning techniques. So this work was conducted as our machine learning course assignment, and let's dive into the outline of our presentation. So this is the outline of our presentation where we'll introduce the introduction, motivation, problem statement, and so on until the results. So let's begin with the introduction. Loan default prediction is very important for financial risk management as it helps lenders to identify risks and reduce losses in a growing lending market. But the challenge is the sharp class imbalance in our data set. So around 11% of the 255,000 loans that are defaults, meaning that they are rare events and hard to detect. So traditional models like logistic regression would struggle to capture linear patterns in financial data. So this is where machine learning comes into play, especially assemblance methods, which can improve prediction accuracy. So in this study, we investigated models like logistic regression, random forest, XGBoost, and a novel stacking classification to solve these challenge and better predict loan defaults. So let's move on to why this matters. Now let's talk about our motivation. With the global lending market expanding rapidly, there's a growing need for accurate loan risk prediction to protect lenders from significant loss. But there would be severe class imbalance where defaults are rare, which makes it hard for models to predict perform well, as they often focus on the majority non-default class. So traditional statistic model like logistic regression also lack the power to capture complex patterns in financial data. So this is why we turn to machine learning and assemble techniques which would offer a promising solution to improve prediction and help lenders to manage risks more effectively. So next, we'll define the problems. So this brings us to the problem statement. Loan default data set like ours are highly imbalanced, making it hard to predict rare default cases. And traditional models often fail because they focus too much on the majority class. So this creates a clear need for a more effective and robust models that are optimized for imbalance classification, making sure that lenders can better identify high risk borrowers. Now let's look at the specific research questions we aim to address. So here's our research problems broken down into three key questions. First, we want to understand how well models like logistic regression, random forest, XGBoost, and our novel stacking classifier performs in predicting loan defaults when faced with severe class imbalance like our dataset. Second, we want to explore the impact of using SMART, a technique to balance the dataset by oversampling the minority class on model training and evaluation outcomes to see if it improves performance. And finally, we examine the trade-off between precision and recall in these models as precision minimizes false positive while recall ensures we catch more defaults, and we'll look at how this trade-off impacts practical lending decisions. So these questions guide our study as we aim to build better tools for lenders. Next, we'll look at our research objective. So this study aims to evaluate how well machine learning can predict loan defaults, especially when dealing with severe class imbalance. So it helps lender to make better decision, and we focus on four key objectives. First, we compare the performance of logistic regression and so on under this imbalance. Second, we assess how smart oversampling impacts model training and evaluation outcomes. Third, we evaluate the trade-off between precision recall. And then finally, we aim to identify the best strategies to balance model performance and real-world applicability in financial risk management. And this here is our literature review summarized in three key points. First, traditional models like logistic regression are popular for loan default prediction due to their simplicity, but they struggle with nonlinear patterns. So this has led to the rise of assemblance methods like random forest and XGBoost, which better captures complex financial data patterns. Second, ensemblement techniques such as bagging and boosting improve performance by reducing errors, while stacking combine multiple models with a meta learner shows even better results, especially for imbalanced dataset. The class imbalance is a major challenge in loan default data and often solved with SMOT. So for evaluation, PRAUC is preferred over ROC-AUC because it is better focused on precision recall trade-off, which is crucial for detecting rare defaults. So this is our taxonomy mapping where we have summarized the most common terms across the 20 academic papers that we have read through. So this ranges from the data, the machine learning algorithms, the features, and also the evaluation metrics that are more commonly used. So, to introduce our data is from a Kaggle dataset of 255,000 records, each with 18 features, 9 of which are numerical, like loan amount and income, and 9 categorical, like employment type. And our target variable is default, where 1 means defaulted and 0 means not. So as you can see, the class imbalance is very clear. Only around 11% are default, while 88% are non-default, as shown in this chart. So this imbalance is a key challenge that we'll address in pre-processing, which we'll discuss next. Now let's talk about pre-processing. To address this class imbalance, we apply SMOT on the training set, balancing it to a one-to-one ratio of default to non-defaults, while keeping the test set in its original distribution to reflect real-world conditions. For categorical features, we use ordinal ranking for ordered categories, converting binary features to numerical, and one hot encode nominal features like employment type. And numerical features such as loan amount are standardized using standard Scala to ensure consistent scaling across models. And this prepares our data for effective model training, which we'll cover next. So this is our methodology. We use supervised classification to predict loan defaults versus non-defaults and focusing on addressing the class imbalance. And we engineered two new features, which is loan to income ratio and stability score, to capture financial strain and stability as detailed in our report. And our models also include logistic regression, random forest, naive Bayes, XGBoost, and then the stacking classifier that combines all these models and apply Bayes' optimization to maximize PRAUC. So evaluation, we prioritize PRAUC with secondary metrics like ROC-AUC, precision recall, F1 score to assess performance comprehensively. Finally, here's our research workflow in a flowchart. We start with data collection and pre-processing, where we gather our records and then apply SMOT encoding and standardization, and then we conduct EDA to understand the data patterns and imbalance. Next, we move on to feature engineering and adding features like loan to income ratio. After that, we develop our model, logistic regression, random forest, XGBoost, and then stacking classifier. And finally, we evaluate them using PRUC and other metrics before wrapping up. So in the following slides, we'll discuss the results section where we explain the results that we have gotten from developing our models.
So moving on to the exploratory data analysis of our dataset, we check for the data distributions of our data, and then we have the correlation matrix heat map, the chi-square test for categorical against categorical variable, and also the variance inflation factor to check for the multi-collinearity of our data. We also have the analysis of like the categorical and numerical variables. And here is our correlation matrix heat map for our dataset. By looking at the heat map, I think we can conclude that the pairwise linear relationships between our variable is not very significant. So something we can observe is that the default and interest rate are positively correlated. So this means that if the interest rate are going up, the default rate is also going up. Similarly, we have default and non-default are also positively correlated, the default and age are negatively correlated, and the default and income are also negatively correlated. There are also other insights which is not very significant, and these are few that we can observe. And next is the chi-square test. So chi-square tests are done to check the significance whether our categorical variable is significantly associated with our target variable, which is the default. So the null hypothesis is saying that the categorical variable is independent of the target variable. But after we did the chi-square test, all the categorical variables p-value is less than 0.05. So we reject the null hypothesis. Therefore, all of them are significantly related to our target variable. We also check for the multi-collinearity in our variables to see if there's any features that are highly correlated with other features. So for now, all variables have VIF value close to 1. So there's no features that are highly correlated. Then we created new features. So it comes to the feature engineering stage. We created features like the loan to income ratios and the stability score, which derive from the existing features like the loan amount, income, months employed, and the long term. So several derived features were experimented, but they are not very good. So leaving us to like these two. After creating the new variables, we also revisit some stage of the EDA, like the correlation matrix heat map and also the VIF to recheck if the variables are highly correlated with each other and to see if they have any relationships between our newly created features and the existing feature. And here now we can actually see that there is some relationships, linear relationships, probably because we derive the features from the existing feature. So the derived features will have some relationships with the features that they derive from. So it's normal. And to make sure that they are not highly correlated with each other, we have to check for the VIF again. And now we can see that some VIF value has increased because of the newly derived features, and but all the variables have VIF value less than 5. So more than 5, it will be a warning. Possibly we will remove them, but then less than 5, it's acceptable. So we'll keep the variables as it is. Now moving on to the feature encoding phase. So for feature encoding, we need to do this because our model cannot understand string. We have to transform the categorical feature into numbers. So there are different types of encoding methods that we use. The first one is the rank-based encoding. So rank-based encoding are done to columns that have some rank-based orders. For example, educations. We have diploma to bachelor's to master's to PhD, like in some kind of rank-based orders. And we have binary encoding. Binary encoding is done to columns that have two values, for example, true and false, or yes or no. And for one hot encoding, basically we did this to columns that have multiple category. We are splitting our dataset into an 80% training set and 20% testing set. We also use a method called stratified splitting, which is to ensure that we have the same proportion of classes in both training and testing. And this is because our dataset is imbalanced. We do not want a situation that there's like less minority class in the testing than the training. We want to make sure both have the same distribution. And now we can move to the feature importance after splitting the data set into a trend and test set. Now, this is the results for our feature importance visualized in a horizontal bar graph. And we use a random forest classifier to find out the feature importance ranking. And here we can see the loan income ratio, which is a derived feature that we built in our feature engineering stage, has the most importance in this ranking, and followed by interest rate, income, age, and others. And we have to scale our dataset also. For models like logistic regressions, nav-based, that actually benefits more from scaling our dataset, while those like random forests that actually don't matter most. But then we have to keep it consistent, so we use a standard scaler to scale our dataset. So one last step before we create our models is to handle the imbalance in our dataset. So we tested with different methods like the careful cross validations and adaptive synthetic sampling, and also others like small ENN. But we find out that small has a better result overall. So we decided to go with small. And for this assignment, we decided to go for logistic regressions, random forest classifier, Gaussian knife Bayes, and also XGBoost classifier for our dataset. Since our data set is highly imbalanced, we use a lot of metrics, different metrics to like evaluate our models. For example, precisions, recall, F1 score, the ROC AUC, and also the PR AUC. So what we do is that accuracy here is kind of misleading because our data set is highly imbalanced. When it predicts more on the majority class, the accuracy will be very high. But that doesn't mean our model is good because it cannot predict the defaulters. So we have other metrics because no single metrics that can tell the full story. So we're going to look at different metrics to see how our models perform. But our main focus is on the PRAUC. Now we are going through the base model results in brief. And here we can see that XGBoost has the highest accuracy among the four models. And it is because XGBoost predicts more on the majority class and predict less of the minority class. So accuracy is misleading here. And now we're going to see other metrics. So these are the results of the precisions. XGBoost has the highest, followed by the random forest and knife Bayes, and also the last is the logistic regression. For the recall results, XGBoost has the lowest compared to others, and logistic regression has the highest recall. For the F1 score, is about precision and recall balance. So here we can see XGBoost has the lowest F1 score. It's because the precision is very higher than its recall. So for other models, it's quite balanced. The highest is the knife Bayes classifier. For the receiver operating curves AUC comparison, all models have more or less likely the same score, with the random forest being the highest in this RSC AUC comparison. And for our metrics that we mainly focus in is the PR AUC, which we'll use for later hyperparameter tuning. So this one, also in here of the base model results, we can see that Naive Bayes has the highest PRAUC, while the others are more or less likely the same, with logistic regressions being the lowest here among the four. So now our base model has been done. Now we move into hyperparameter tuning to see how if our models improve by roughly tuning the parameters a bit. So in our hyperparameter tuning, we use a library called Optuna, and Optuna need metrics to know if our model improves or not when it automate the process of hyperparameter tuning. So we select a metrics called PRAUC, which we talked about just now. And PRAUC, unlike we just select a recall or a precisions, unlike recall, it will consider like both precisions and recall, and it will evaluate the model ability to distinguish the positive class. So this is one of the example that we compare for the base model of logistic regressions versus the tuned model of logistic regressions. And we can see that heavy metrics in logistic regression has improved by a little bit. So I see that as a significant improvement. For our random forest, the base versus the tuned one, the accuracy and precision drop a little bit, but trade-off, the recall has improved significantly. And also the F1 score, RUC, AUC, and also our main score, the PRAUC has improved. For naive Bayes, pretty much the same as random forest. The accuracy and precision dropped by a little bit, but the recall has significantly improved. So initially, the XGBoost recall is very low, like probably around 0.2, 0.19. And now the recall is around 0.6, which is a significant improvement. by just trading off a little precisions. And the F1 score, RUC, AUC, and also the PRAUC has improved. So the final thing we will do in our project is to stack the models and also select the final model. So stacking model is basically combining multiple machine learning models together, different models together to build a stronger final model. So it will leverage different model strength and also cover their weakness. So here we are trying to stack three models, which is the naive Bayes, the random forest, and the XGBoost. We will use the best hyperparameter that we found during our hyperparameter tuning. And for our final estimator, or what we call as the meta model, we will use a logistic regressions. Of course, we can use other models also, and we can try out different models for our meta model and the stacking model. But for the time being, we use logistic regressions because it is a relatively simple model and also easy to interpret, which is a very suitable model for model stacking. And now we compare the PRAUC of the stacking model and the others model and the base model. And we can see that the stacking model has improvements on PRAUC among all the other models. What is the difference between stacking tune and stacking untuned here is that the stacking tune we use hyperparameter tune logistic regressions, while the stacking untuned is that we use a base logistic regressions for our meta model. So we can see that the stacking with the tune logistic regressions has the better overall PRAUC. For the recall comparisons, the stacking with the tune logistic regressions final estimator has also the best recall among all the other models. So this is a confusion matrix for our final model selections. We will select the stacking tune as our project model, and this is the confusion matrix that it predicts. I wouldn't say it is a very good one, but it has room for improvements, and this is what we get for the moment. So now let's conclude on what we did in our projects. We have an imbalanced dataset, and this imbalanced dataset actually pose challenge in the model training. So during our project executions, we also see like how other people did this same dataset because they pose it in Kaggle, right? So we actually survey like how they do, and then want to apply to our projects. Then we found out that some of them actually did some wrong steps. For example, they oversampling the test, which caused data leakage, and then their results were very good. But I don't think that is a good solution. So, uh, and I see that some people that actually did the right steps one, they actually got the same the results as mine, and there's some less or more the same results. So probably there is some problems, original problems in this data set, but I think there's still room for improvement that we can improve a little bit more. And the model is decent here, and there's a room for improvement. I wouldn't say it's good. And the model can be further tuned for specific use case. Like for example, if you want the recall to be higher than mine, you can actually tune threshold tuning so that you sacrifice the precision for more recall. If you think that precision is more important, you can do that also. And I would say that the data set might have some limitations, but we will look further into that in our future projects. That is all for our presentations. Thank you.